Today, we are honored to welcome Dr. Rosen, who shares with us to discuss NISAR, a landmark in U.S.-India space collaboration, one of the most ambitious Earth-observing missions ever undertaken jointly between NASA and ISRO. Together, we will explore how this groundbreaking mission exemplifies the future of international cooperation in space. Where two leading scientific and technological nations combine their strength to advance research, develop new capabilities, and generate knowledge and benefits communities around the world. As we look to the future, we must also reflect on the past. We owe a great deal of gratitude to our founding chairs for their commitment to fostering the development of the India Center and for making today's distinguished lecture possible. It is now my great privilege to welcome the Indian Community Endowed Chair and Director of the India Center, Dr. Yogesh Joshi, who will introduce the moderator and speaker for today's event.
Thank you, Rana. Good afternoon, everyone. It is my distinct pleasure to welcome you all, students, faculty, UCF leadership, and community members to the annual distinguished lecture hosted by the India Center at UCF. As director, I'm especially proud to lead an institution that is an incubator of ideas, education, and research on contemporary India at UCF. Today's distinguished lecture on NISAR, a landmark in US-India space collaboration, comes at a pivotal moment that the global space landscape is evolving at an unprecedented pace. We are gathered here to explore how the confluence of ideas, technological progress, and international collaboration between the world's strongest and its largest democracies can drive innovation, foster development, and solve the challenges of our times. This is the second distinguished lecture of the India Center, a program we launched last year. While this series has quickly become our marquee event, this year is particularly unique for two reasons. First, the theme of today's lecture dovetails perfectly with the India Center's mission to study contemporary India and its rights, while simultaneously leading into UCF's core competency in space research. Second, this event represents our deliberate plan to build robust partnerships both within the UCF and beyond. We are incredibly fortunate to partner with the UCF Space Council and the Florida Space Institute for this lecture, taking a significant step in our collaborative journey. I would like to begin by expressing my deepest gratitude to the interim dean of the College of Sciences at UCF, Dr. Josh Caldwell, for his constant encouragement, help, and support to the India Center. His leadership has been a constant source of inspiration, and we continue to grow our mission here at UCF. I'm also very grateful to Dean Caldwell for doing double duty today and moderating this event. As a Pegasus professor in the Department of Physics and a world-renowned planetary scientist, there is truly no one better suited to lead this discussion. Anyone who has interacted with Professor Caldwell finds his passion for space exploration and commitment to academia contagious. He's a steadfast supporter of the India Center, and here is one of my favorite things about him. He's deeply interested in the vital issues intersecting science and policy. Dean Caldwell holds a Ph.D. in astrophysical, planetary, and atmospheric sciences from the University of Colorado at Boulder. Thank you, Dean Caldwell. What many of you may not know is that Dean Caldwell has been an integral part of this distinguished lecture from its very inception. When the India Center first considered inviting Dr. Paul Rosen, I turned to the Dean for his perspective. Without hesitation, he personally reached out to Dr. Rosen to make today possible. This connection is not just administrative. It is deeply rooted in their shared scientific contributions and achievements. Their research careers have long intersected in the study of second rings, showcasing the incredible strength of academic networks. It is with immense pride that we welcome our distinguished guest, Dr. Paul Rosen. As the project scientist for the NASA-ISRO Synthetic Aperture Radar mission at the Jet Propulsion Laboratory, Dr. Rosen is at the heart of the most significant space partnership in the history of our two nations. Dr. Rosen is a titan of space research, holding a Ph.D. in electrical engineering from Stanford University. With over 3 decades at Jet Propulsion Lab, his work has defined the field of interferometric radars. He is widely considered a doyen in the field of NISAR, interferometric synthetic aperture radars, the technology that allows us to use radars not just for images, but as a high precision stethoscopes to measure millimeter level changes in the Earth's crust. From leading the shuttle radar topography mission, which created the first high-resolution 3D map of our world, to his current leadership of NISAR, Dr. Rosen has been a tireless advocate for open science. We are particularly honored to have him here following a historical 2025, the golden year of US-India space cooperation, which saw 2 major deliverables. On 30th July 2025, the world watched as India's GSLV rocket lifted off from Sriharikota, carrying the NISAR satellite into orbit. This 1.5 billion marvel is a scientific handshake between NASA and ISRO, monitoring our planet with sub-centimeter precision. Crucially, this mission pioneers open science by providing its massive daily data stream free to researchers and policymakers worldwide. We also saw the historic milestone of an Indian astronaut joining the crew of the International Space Station in 2025 as part of the Axiom mission. US global leadership and India's rise as a major power are based on shared values and mutual strategic partnership. Dr. Rosen's unique perspective as a leader at the intersection of NASA and ISRO illustrates the immense potential of our 2 nations' technological ambitions. At the UCF India Center, we are forging a path to breakthroughs that benefit our community and the world. We live in a new digital age, but we are also at the cusp of a new celestial era. And as we navigate these interesting times, UCF remains at the forefront of nurturing an environment where transformative research takes root. It is now my pleasure to invite our moderator, Interim Dean Josh Caldwell, to lead our discussion with our guest.
Thanks very much. It's a privilege to welcome scholar and leader Dr. Paul Rosen's caliber. As Yogesh mentioned, when he approached me about this distinguished lecture, he said, well, there's a space scientist at JPL, and you're a space scientist, and you've been to JPL, maybe you know him. JPL has thousands of employees. And I'm like, I'm not going to know this person, but who is it? This is Paul Rosen. I'm going to tell you this because Paul is not going to tell you, but Paul Rosen is a famous name in the study of planetary rings. When I was a graduate student, I learned about the Rosen waves. These are waves in Saturn's rings that were discovered by Paul as a graduate student. And then some years later, when I was working on the Cassini mission studying Saturn, we were studying these waves, and my graduate student worked on these waves and others that we discovered in the Cassini data. I'm like, is it that Paul Rosen? And I checked, it was that Paul Rosen, who I had actually never met in person until today. And one of the wonderful benefits, as Yogesh was alluding to with academic networks, is by having someone of Paul's caliber show up, I got to see some of my former students and even current students who are quite difficult to be lured to my office these days, but with Paul there, we managed to do that. In a world where scientific discovery and technological advancement are deeply influenced by national and international policy, Paul's expertise offers invaluable insight, and few individuals are better suited to illuminate the significance of collaborations like the one that we'll be talking about today with NISAR mission. It is with great honor, enthusiasm, and anticipation that I invite Dr. Rosen to deliver today's distinguished lecture, NISAR, a landmark in U.S.-India space collaboration.
Thank you, Dean Caldwell. Thank you, Dr. Joshi. It's a real pleasure to be here in Florida at the India Center to give this lecture. I've been going to India now for almost 15 years to build this mission. And in that time, I've traveled, I think, 35 times to India and back. And it's been a privilege and a pleasure to be able to do that. I have to tell you, since we launched the satellite, I've had many fewer opportunities to go to India. received the invitation to come here to the India Center, I was really thrilled because it's a little bit like going to India. So thank you very much for this invitation. It's a great pleasure to talk about NISAR. I hope you don't regret inviting me because I talk a lot about NISAR, and I may talk a little bit more than you would like to hear. But let's get started. I'm going to try to take you on a journey of development for NISAR. I usually talk about technical things, and I know many of you don't care very much about the technical aspects of NISAR. I'm going to try to show you the highlights of what this system is. It really is a landmark in many senses of the word. It's a landmark in time, it's a landmark in the scope of what we've tried to accomplish. And sometimes with these large endeavors, we look back and say, did we really do that? And I kind of feel that way with NISAR. So hopefully you'll get a feeling for the scope and scale of what we've accomplished with NISAR. Yeah, we did do a distance check. So in the next little bit less than an hour, I hope, I will cover these topics. I'm going to give you an overview of NISAR. I'm going to give you a little bit on the genesis of how the collaboration started, because I think many of you might be interested in that. The elements of the collaboration, the whole development journey, and all the kinds of things that we encountered in working together on two sides of the Pacific, literally on opposite sides of the Earth. And then I'll say a little bit about our first year of operations, and a few words on perspectives. All right, so this is an animation that our animators made in 2016 of the goal. We wanted to launch this satellite and do Earth science like we've never done before. This was made from web views of the GSLV-2 launch vehicle in 2016. Hopefully this will. And this was the actual launch. It looks kind of similar. I hope you agree. And this occurred in, could you hit the animation? I had the great privilege of being able to be there for the launch, and some people can take their phones and take a picture of the launch. This is an enormous rocket with a 4-meter fairing and a 2,600 kilogram payload on top of it. And we're some kilometers away watching it launch in the distance. If you listen to the end of this, somebody says, "See you later, NISAR." So let's go on to the next slide. All right, so what did we launch? This is an animation that we made many years ago also, depicting what it is that we built. And ISRO provided this launch vehicle, the GSLV-2 launch vehicle. They provided the spacecraft, and NASA provided the large radar instrument structure and the electronics for one of the radars that we put onto the spacecraft. So after the launch at 5:40 p.m. In the evening in India, it took about 20 minutes to get into our orbit from this launch vehicle, such that we could have a 6 p.m. orbit. We are in an orbit that is sun-synchronous, which means it's always 6 p.m. on the Earth whenever we're observing in the evening at 6 a.m. on the other side of the Earth as we come down. So you'll see in a minute the spacecraft, the instrument come into view. Here's the spacecraft. The solar panels were deployed right away so that the system could have power and generate power and keep the batteries charged. We rotate the spacecraft a bit to keep the temperature appropriate. And then we have to begin a deployment of a huge reflector. So here we go. The reflector is stored in that cylinder. It's about 2 meters long and about 3/4 of a meter in diameter. And that has to be released at the end of a 9-meter long boom. And the boom had to be built in such a way that it wrapped around the spacecraft and fit inside of the fairing of that rocket. All these steps are very high precision, and boom and reflector have to be stable to millimeters in order to do the measurements that we want. Here we're rotating around in order to keep everything nicely warm, and then we deploy the reflector. It's a 12-meter diameter reflector, a huge instrument in space at the end of this 9-meter boom. It's made out of gold-covered molybdenum mesh, very lightweight and needed for this particular design. So that's what we built together. And we launched it and we're operating it together. Next slide, please. So we built this radar. It's called the synthetic aperture radar. It's a highly technical thing that even people in the radar field don't always understand. So I'm going to show you another animation that gives you a flavor for what radar is. We have a long radar, a light wavelength. It's in the centimeter range. And when you have a long wavelength with a structure that's about 12 meters in size, and you shine that flashlight on the ground, it creates a spot on the ground that's about 20 kilometers in size, as you can see here. A very large spot. And if you wanted to get an image out of that, you would have a 20-kilometer resolution image. Can't see very much with that. So what we want to do is create a synthetic antenna that's 20 kilometers long in order to focus down to a very narrow resolution image. And we do that using this technique called synthetic aperture radar, where we fly along the track and take observations 1,000, 2,000 times a second. And each one of those observations we can think of as an element in a very long antenna. So if you hit the animation, you'll see we fly along, and any given point on the ground, you see that little green dot in the top right. That is a point of reference, and as we collect more and more of these very broad pulses, we can assemble them together and create a high resolution image. So that's what synthetic aperture radar is. We can go on to the next slide. What's so great about synthetic aperture radar? Why did we want this for this particular mission? What are we trying to do with it? Well, SAR and radar in general operates at a long wavelength compared to optical imagery, which is at micron-sized wavelengths. So we're seeing very, very different things with the radar than we're seeing with optical imagery. First of all, we can see through clouds. We can see at night because we have our own illumination source. We don't have any restrictions, so we have very reliable imagery. And we can see things that are structural and electrical as opposed to chemical, which is mostly what we're seeing with the optical sensors. That's just a broad generalization. Optical sees structure too sometimes. But you can see on the right there, oops, going back. Yeah, you can see on the right a picture of a radar image that's cutting a swath across a desert in Sudan. The orangey colors, those are from optical image. All you can see is the sand sheet. The radar with its long wavelength doesn't see those sand particles. It penetrates right through them, scatters off of the surface below, which happens to be a buried river channel, comes back through the sand, and then is received by the radar, and we can form these high-resolution images. So it's just one of my favorite examples of how the radar is fundamentally seeing something very different from what we see with our eyes. In the middle, you see those beautiful, what we call fringes, color patterns. That's actually measuring from one time to the next how much the ground has moved down to millimeter precision. That's a signature of a volcano erupting. So as the Earth deforms or subsides due to lava movement, we can measure that change of the surface in image format at very fine resolution and understand what's actually happening at depth. And on the left, that's also volcanoes. These are not active volcanoes. But that's using the different orientation of the radar wave, which you can also control, to understand the structural content, whether it's vegetated or not vegetated, whether there are buildings there or not, so we can classify Earth using these techniques. Very powerful, multifaceted tool for our science objectives. And if you go to the next slide, I'll show you a few of these things. So hit go again. So here's an illustration of the kind of science we want to do. These are data that were acquired by another satellite, animated for your viewing pleasure, because these were made before NISAR actually launched. We fly over once and we make these radar images, and then we're going to fly over again 12 days later and make another image. And we'll do it again 12 days later, and keep flying over it and create a time series of images that we can interfere with one another and see how the Earth is moving over time. This happens to be data that was acquired over the Central Valley of California, where water is being extracted to use for irrigation in farms. And as the water is extracted from the aquifer compacts, and all of the soil above it sinks. So what you're seeing here is roughly 70 centimeters of compaction or subsidence of the Central Valley in about a year's time frame through this interferometric technique that we've developed over the years, and that NISAR is now executing all over the world. Next time step. Here's another example that's near and dear to my heart. Hit go. This is over Los Angeles. You can see that it's sort of breathing in the Orange County area of Los Angeles. It's going up and down over every year as water is extracted for irrigating lawns in the summertime and then re-injected in the winter to recharge the aquifer. The ground is going up and down by about an inch all the time, every year. And in some of those places, it's actually subsiding continuously and just sinking. So it's very important for understanding infrastructure in the Los Angeles area. It's important for understanding aquifer health, and the physicists are also very intrigued by how the water interacts with the fault lines, which you see there in red. We have a lot of earthquakes in California, and if water is controlling them, we need to understand how water is controlling them. So these are just a couple of examples of how we can measure this deformation. Next slide. All right, next, hit the go. So this is using the radar reflectivity, the polarization, to be able to interpret what's going on the ground. This is the Amazon. And in the Amazon, we have lots of forests. We also have lots of deforestation. We also have a lot of inundation during the flooding periods of the Amazon. And all of these things affect the carbon cycle. The loss of forest vegetation, the decomposition of materials that are in inundated areas every year. These are important for understanding the exchange of carbon with the atmosphere. This map that you're seeing here was made from an international satellite. It took about a year to construct it. In case of NISAR, we'll be making a map like this once a week for the life of the mission, of not just of the Amazon, but of all ecosystems around the world. So if you really want to capture the carbon budget on a global scale with looking at above ground biomass, which is the least known in the carbon budget, this NISAR is the way to do it. Next time step, please. The third, so we've covered sort of deformation, we've covered biomass and ecosystems. The third area is understanding the cryosphere, the exchange of the exchange of energy between the oceans, the atmospheres, and the ice sheets themselves. This happens to be a ice cap in Iceland where we flew an aircraft to make these kinds of repeat pass measurements. And from those repeat pass measurements, we can map the velocity field of these ice sheets, which I hope you can see in these conditions here. This is going to be done on a monthly basis for all of the ice sheets of the Earth, Greenland, Antarctica, the mountain glaciers also in the Himalayas, as well as other mountainous regions around the world. So we will have a much better understanding of where ice is accumulating and where it's depleting to understand the total budget in that regard relative three main pillars. You can imagine with a system that, next time step please, you can imagine with a system that has day-night and all-weather capability, this would be useful for a whole host of applications. So this is very technical, so I'm not even going to read it at all, but the only thing I want to point out is the top two items, which you can see here. The L-band 24 centimeter wavelength radar, NASA JPL built that radar, and the reflector, the boom, and the structure, those are all NASA, so the reflector, the boom, and the structure. This animation here is just to tell you it's really complicated, this radar, so that's all you need to know in this talk. And ISRO built the S-band version of that radar, and they built it to the same technical specifications. So both radars do this very fancy method called SWEEPSAR. They do it in synchronicity, so they are working together. We send a timing signal to them so that they can time when they send their radar. Everything has to work down to, microseconds worth of precision here. So it's really critical to get all this right. So that's what I want to say about this slide. We can go on to the next one. Yeah, and this tells you the scope of what we're trying to accomplish here. We want to cover the Earth because we're looking at variable and sometimes random phenomena. Earthquakes, you never know when they're going to happen. Volcanoes, when they're going to pop off. And you don't know where deforestation is going to happen in advance. So we wanted to design a system for science that is reliable and delivers us the data wherever these changes are occurring. That meant complete Earth coverage and complete ice coverage. We don't cover all the oceans, but we do cover all the land and the ice. And we cover it as we go up the orbit, and we take data when we go down the orbit the other side, which means that we get 2 samples of the Earth every 12 days at different times, depending on where you are on the Earth. So that's a lot of data, and we had to design a system that could acquire, store, and send to the ground all of this data. And we have 2 constituencies. We have the US constituency, and we have the Indian constituency with different requirements for coverage of these 2 instruments. So in light of that, if you go to the next slide, oh, so not quite there yet. That's all right. If you think about it, we had to have 2 downlink systems on board, one for going to the US and one for going to India, and these were both extremely capable, orders of magnitude more capable than previous systems, and they had to be developed specifically for this mission. Okay, so now I'm going to talk about the genesis of this a little bit. So that's what NISAR is, and I hope you got a sense for the scope of what NISAR is. Now I'm going to talk to you about how we got there. So in 2007, NASA received guidance from the National Academies of Science, Engineering, and Medicine that they should do a mission like this to cover these science disciplines I just talked about: solid Earth, cryosphere, and ecosystems. And they specifically said it should be doing repeat pass INSAR in order to make these measurements. And some of that had to do with us telling the community in years before that this is the way to do it. So that was the recommendation. NASA asked us to study a mission to do this, and we tried for many years to try to make this work. But because of cost issues, programmatic issues, we just were not succeeding until the year 2011. So next slide, please. And I just want to say the community itself in the US had been waiting for a system like NISAR since 1978. CSAT was the first civil SAR system. It was an L-band SAR, launched in 78. It operated for 3 months, and then the power system failed. But it revolutionized our thinking about what one can do with a synthetic aperture radar. And the community had been trying for 40 years to get another system in place. So that's what the technical survey was recommending. So now a little bit about the collaboration between NASA, JPL, and ISRO. This partnership did not just grow out of a vacuum. We have already been working with ISRO on many things. In fact, NASA had been working with ISRO in its inception 50, 60 years ago on rocketry and that kind of thing. But in more recent years, we flew a hyperspectral instrument on the Chandrayaan-1 moon mission, and that was the instrument that discovered potential for water in the south pole of Mars, of the moon. And that was a very successful collaboration. If you go on to the next slide, there was support in INT by our team in India, so it was our first experience with working with the Indian space community, and we learned lots of lessons about how we can work together. Go to the next slide. We also, in the time frame of early discussions with NISAR, we were working on supporting the Mars mission, Mangalyaan, with the telecom system, and I think that actually did occur before the Mars missions. So lots of experience already, and in fact, in Earth science, there were some partnerships in understanding what's called scatterometry data, ocean wind measurement data. Next slide, please. So in the space radar area, synthetic aperture radar area, JPL has a very long history. You can see some of the missions on the top here. And SAC, the Space Application Center at ISRO, also had a history of missions. Chandrayaan-1 had a radar on it that actually was built by the US, but India participated in its integration. This is the scatterometer mission that we partnered on data analysis with ISRO on. And this RISAT-1 mission was a different wavelength synthetic aperture radar that was launched in 2012. So ISRO had experience in this area, and they also worked with the French on a Ka-band radar. So the combined experience of JPL and ISRO in space radar already was made this partnership an attractive feature. Next. So this is sort of the description of what happened. Our program officers were in touch with their colleagues at ISRO whom they knew. They talked about it and said, yeah, maybe we should explore this. They sent somebody to India in 2011, December 2011, that would be me. And we talked with them about our concept. And they were extremely interested in it. I happened to have been talking with other colleagues who had been going to India and had been talking about having another radar frequency, S-band frequency, rather than the L-band frequency that NASA was looking at. ISRO wanted to build the instrument. JPL wanted to build the instrument. So we had a challenge in trying to come to an agreement. After several months, I suggested, why don't we build two instruments? The system is designed so that we can probably fit both an L-band and an S-band radar on the same platform. Our engineers looked at it, they said, yeah, it looks like it's feasible, it shouldn't be too hard. It was hard, but we made it work, and that was the thing that allowed us to go forward with the mission. That was early 2012. It still took close to 3 years, two and a half years, to allow the program to go forward, mostly because of working out technical and programmatic funding issues. But it wasn't until Prime Minister Modi was elected and President Obama were meeting, and they needed to have something that they could hold up as an accomplishment. And we happened to have a lot of paper that they could just look at. And they were very pleased with that. So that was the start of, we were very lucky. It was the start of the NISAR program. Next slide, please. So the first real workshop, we had many meetings before 2014, but the first real workshop was held in 2014 when we were an official project. Some of you may know some of the people on this slide, that's why I included. You can see me in the top. This is what I looked like when I hadn't lost all my hair and hadn't grown a beard. This is the current director of this Space Application Center. He's been a strong advocate over the years. At this time, he's not director. This was the director at the time, A.S. Kiran Kumar. He was the chairman of ISRO for many years, some of you may know. And at that time, we started building our relationships. These are mostly scientists and data processing people. But we have thousands of pictures like this from all of the meetings we've had, both on the science side as well as the technical engineering side. I can't emphasize enough the importance of the social aspects of building a mission like this when you can't be together all the time in the same room. You have to build relationships personally when you have the opportunity. And fortunately, NASA has had enough funding and let's just say government support to send us to India. It was very difficult for Indian engineers to come to the U.S. except during the integration period. So it was usually us going to India, which we didn't mind too much, but it would have been nice if India could have come here a little bit more. Next slide, please. So now I'm going to talk about some of the elements of the system. One of the important elements from a scientific perspective is both the two radars. We have two radars that have equal capability, one built by India, one built by NASA. And having two different wavelengths allows us to see different things than if we have just one wavelength. It's like seeing things in black and white versus seeing things in color. And this is just an example you can see here of one particular kind of terrain. This is wheat fields. This is the palm forest, rubber plantation. You can see that the signature in the radar imagery of these two is extremely different. And so if you want to classify land in a more precise, accurate way, the more frequencies you have, the more polarizations you have, the better. So with NISAR, we have pretty much the best you can do with this system. Next slide, please. So just to give you a sense for the scope of this endeavor, there are many elements that NASA is doing and many elements that ISRO is doing, and these are the organizations that are involved on both sides. So a project of this scope needs to be coordinated from a headquarters level, from a main institution level, that would be JPL, but in ISRO they had involvement of the spacecraft people, launch people, the instrument people, the mission operations people. So many, many centers are involved on all sides. It's very, very complicated to coordinate. Next slide. And this just shows you the hardware breakdown. Again, very technical. I don't want to go into great detail here, but you can see that there's the SARs at the top here. There's engineering payloads in the bus. There is the downlink system I mentioned before, one for the L-band data to be downlinked and one for the S-band data to be downlinked. And there's the data processing. We've done our utmost to make the products that are produced by ISRO to be as close to identical to the products that we produce from the L-band data. We have no requirements on the S-band data, but of course we want the data and we'll probably be processing them too. And having a community downloading data from one facility and getting a different answer from a different facility, we don't want that. So we've done a lot of work to coordinate that. And then the science teams, of course, are doing joint science on all these fantastic data. Next slide, please. Again, a highly technical slide. The point of this slide is showing you is that it's really very integrated. Everything we do has to be coordinated. I was participating in some of the deployment activities, and every step at every minute was choreographed and mapped out for the entire period of time. And people were sitting in India, people were sitting in the U.S. on headsets, talking through every step of the way. This happens also during operations on a routine basis. There has to be strong coordination because the spacecraft can't make a mistake, because we've got to collect all this data. So as you can see, very complicated, two different downlink systems, coordination of the actual commanding for ISRO to send the commands up to the spacecraft. Next slide. All right, those are the elements of the collaboration. very complex and has to be highly coordinated. Now a little bit more on the development journey. Next slide, please. These are just mostly pretty pictures, so hopefully you enjoy those. Part of the coordination activity is meetings. So we have weekly meetings with India on the science side, and similar for the other technical disciplines. So 260 telecoms. An FTM is a focused technical meeting. We call them focused technical meetings instead of other names, so that not too many management people would come to the meetings. And that means then that people could relax and speak freely at a technical meeting rather than worry about what their managers were going to say. And I think that worked mostly. We had many exchanges. This is a poster session at one of our science meetings. And here's a meeting with students that we had for outreach activities on the science side. We also did field work. This is in a lake area, a dry lake area near Ahmedabad, where we did some soil moisture measurements. So it's not just building the hardware, it's also meeting with people and doing science, getting the science going. Next slide. And in addition to just interacting with each other, we have to inform the community. And we've had many, many workshops in the United States and also many in India as well. You can see this is a big workshop we had in Pasadena. This is the equivalent workshop that we had in Ahmedabad in 2023. So lots of community outreach to build the community. The SAR community in the United States is quite a bit more mature than in India. And one of our goals, one of ISRO's goals, has been to increase the capacity of using these kinds of data in India beyond just government use. Next slide. And one of the things that we did that was really critical in cementing our relationship, both on the engineering side and on the science side, was to bring a test-bed instrument, an airborne version of our spaceborne mission, to the United States and put it onto an aircraft that we use for our own radar system. This was quite an accomplishment. It was almost as difficult as building the spacecraft itself. To get all the permissions, get the hardware here. This was done before and after the COVID period. And it was really essential. We flew up over 200 flight lines in the United States to collect data. India was extremely interested in this because it turns out that flying airborne radars in India is prohibited by the Ministry of Defense. And so they could not get any data to do the kinds of studies they needed to prepare for the mission. So these data turned out to be essential for that. So this partnership got us to know their hardware engineers very well as their scientists, and helped greatly with the development of the flight system. Next slide, please. We also rehearsed. I mentioned all of the commanding that was needed for running the deployments and all of the various stages of the mission. These were rehearsed many, many times. ISRO did not understand why we had to rehearse these things as many times as we did, and we probably didn't. But we did, and they agreed graciously to do it, and we ended up with a flawless execution on all of the deployments. The commissioning of the spacecraft went really, really well, I think thanks to all of that preparation, both in India and across the Pacific. Next slide. The integration journey was really challenging. We built a mechanical structure, that cylindrical octagon that you saw with all the electronics on it. The bottom three sides of the octagon were decoupled from the top five sides. That's where the S-band electronics would be integrated. So we built the frame, we shipped it to India. They integrated all of their electronics on it and tested it, put it back in the box, shipped it back to the United States. Then we integrated that with all of the other things that were coming together onto the the structure into one element, and we integrated in the reflector and the boom as well. There are other units here that have to be built. Meanwhile, the satellite was being built by a different center, and the boom had been tested with a mock-up of the actual structure here. This was done earlier. All of these elements had to come together here. Once it was fully integrated here and the spacecraft was done, then we shipped all of this in a much bigger box to India, and that had to be integrated with the spacecraft. And actually, I'll show you some slides. There was another step in between this and launch, which was unfortunate, but also part of a tight partnership. And maybe it's on the next slide, perhaps. Okay, no, first, so once they shipped their instrument to us, we discovered, once we integrated it, when we turned on the L-band radar, the S-band radar turned off. This was a big problem. So it took a long time and a lot of patience on both sides to figure out how to get these two radars to talk to each other. The issue was that there was excess radiation in the environment that was being emanated by all the boxes, and some of that radiation would leak in and affect the control electronics. So we had to do shielding, all kinds of things to mitigate that problem. But with patience and partnership, we ended up solving it all. Next slide. This is just a pretty picture I thought you might appreciate. It's a thing of beauty to see these things come together. There's literally maybe kilometers of cables that have to be put into these things. Everyone has to be routed and tested. It's just an amazing amount of work. The reflector itself and boom testing is very important. It has to go through thermal and vacuum type of testing in various chambers. This was at JPL when it was fully integrated. Next slide. And then it all had to be put into that very big container that I mentioned. The only aircraft that could carry it was a C-17 Air Force transport aircraft. So that went there and was received graciously by our Indian colleagues and then put into the India facilities, beautiful facilities, world class, much better than what we have at JPL, I have to tell you, for integration. Next slide. So this was the journey to go from this drawing you see on the left. Sorry, I keep pointing it back and you're looking up here. This drawing on the left to the actual realization on the right. This should have been the end of the story, and then we just integrated it to the spacecraft. It turned into the launch vehicle. Unfortunately, it turned out through testing at ISRO, as well as our own testing at JPL, we discovered that the reflector had an issue. And it had a thermal issue. It was going to get too hot on one side and soften up, and it might not deploy properly. And that would be a disaster, $1.5 billion down the drain. So we ended up taking the reflector off after it was fully integrated, almost ready to be put onto the launch vehicle, and shipped it back to the United States for mitigation. That took 8 months and an enormous amount of patience from our Indian colleagues. They really wanted to get this thing launched, and unfortunately it took a while. Next slide. So after that mitigation, as we call it, you can see the black reflector on the left went to a silver covered reflector on the right. I like to say the solution was to apply duct tape, which is the typical engineering solution. It was actually silver Teflon tape, very reflective tape that reflected the sunlight away from the carbon fiber. All right, next slide, please. This is more of the same, they're just pretty pictures. Next slide. All right, so then we launched. I'm not going to play the launch again, so if you could hit the next slide, keep going. This is the upper stage, a view of the upper stage firing. This was a 20-minute burn. Anyway, that was a very nerve-wracking period that it worked beautifully. This is actually a video of the deployment itself taken from the spacecraft. That is the deployment of the reflector, the thing that we were most worried about because of that thermal problem. And as you can see, we blew it out. It's now being pulled out by a motor. There's cables that wrap through the entire structure and then pull it out to its final form. And this also was a little bit nerve-wracking, but you can see that it's working very well. It's actually working better in orbit than it worked in testing on the ground. It's really great. And there's an interesting story about the cameras too. JPL usually doesn't put cameras on board because they just don't think it's necessary. We have other things, other ways to measure it. But ISRO insisted they had to have cameras on. These are ISRO cameras. And we're so happy that ISRO put the cameras on the spacecraft. It really is a great view to see that. Anyway, we can take the next slide. Oh, actually, that little thing in the corner, that was actually a picture, image of NISAR in orbit, taken by an optical satellite that was happened to be whizzing by 100 kilometers away. So it actually is there. We have evidence that it's actually in orbit. Next slide. The deployment was successful, as you saw. We were all very thrilled, and that was what, after that, we can start our radar operations. Next slide. All right, so now I'm just going to show you a few pretty pictures of what we've acquired so far. It's only been 6 months since we've really turned the radar on, and many of these may not mean much to you, but I think they're quite colorful, and maybe you'll enjoy them. Next slide. We did commissioning during this first year. That also went very, very smoothly, thanks to all the planning we did in advance. Next slide. We celebrated 100 days in orbit by having a 100-day celebration in Bangalore with all the leads. Next slide. And here's some imagery. So this may not mean much to you, but this is a 240-kilometer swath image. So in one shot, as we're flying along, we map 240 kilometers. The green colors here indicate vegetation using our polarimetric signature. The purple colors indicate relatively flat surfaces, and the lighter colors indicate urbanized areas. So in one snapshot, we can just sort of characterize in a synoptic way this area. And remember, we're collecting these things continuously and cover the entire Earth in 12 days from 2 different vantage points. If you drill into a very small area in this enormous image, this is what you see. You can see streets, you can see buildings, you can see incredible levels of detail. It's at around 5-meter resolution. There are radars that do much better than this, but I can tell you they don't get a 240-kilometer synoptic view of the Earth at the same time as their fine resolution. So it's really, this is the radar data, this is the optical data. You can see that we're seeing very different things, but the main features are quite similar. Next slide. And the S-band data, the S-band radar is working beautifully as well. This is a comparison of the L-band at the top and the S-band at the bottom, colorized in a similar fashion. And of the same area, this is the same river. I think this might be the Southern Lati, but I'm not sure exactly where this is. And it's a little dark because L-band is long wavelength. When it's a very flat surface, you don't get a whole lot of return. The S-band is shorter wavelength, it's brighter. You can see it's brighter here. But you can see that they don't have exactly the same information. A lot of it looks the same, but a lot of it doesn't. And that difference is what really gives us the new information that we're getting out of this 2-frequency radar. Next slide. This is a beautiful image of an area that's inundated. The areas that are yellow here are not inundated. The dark areas here are just water, and these sort of purpley areas are inundated vegetation. From this, you can make hydrological maps and understand where the surface is inundated and where it's not, which is very important for understanding environment. Next. This is a beautiful image of an ice stream. This is down in Antarctica, or can't tell exactly where, somewhere over here, but this big image here is a blow-up of this little feature here. what you're seeing in these ice streams, this is ice flowing along lines, just the way water would flow down a mountainside. And it's flowing around the topography of the land underneath the ice. So this feature here happens to be a little hill, and the ice is flowing around it. And these eyelash-looking structures here are crevasses, cracks in the ice that have formed because the ice is being deformed as it goes around that structure. So it creates these beautiful patterns. The colors here are either surface scattering, which is this purpley color, and the green is penetration into the ice, scattering from below the surface. So it tells you a lot about the structure of the ice as well as its motion. Next slide. I think this might be the last example. So this is a NISAR example of deformation. I showed you some earlier from other satellites. This was our first real signature of deformation that was acquired in November, it looks like. And this is a volcano that is erupting in Ethiopia. The magma is starting up here, and it's going underground in a lava tube to an eruption site down here. So this one image was taken on November 22nd, one was taken on December 6th. In that time frame, the surface deformed, meaning it subsided as the magma left this area, and it erupted here and created a big jumble. That's basically ash falling down the surface, changing the surface characteristics. This image, this pair here, 1110, which is before this period, to 1122, which is that period. So this is the pre-eruptive period. You can see already it's starting to lose magma from this area, and it's starting to bulge in this area before it actually explodes. So we're making these measurements once a week for the life of the mission everywhere. So wherever these kinds of deformation features occur, we will be tracking them, and then we can understand better the plumbing of the magnet systems, the stresses and strains in fault systems, as well as aquifer health and other kinds of things related to deformation. Next slide. All right, so that's it on that. I have one slide on perspective. Next slide. So I can't read from this distance, so I'm going to look this way. So this is first of a kind science, not because we haven't made these measurements before, but because we've never had this kind of spatial and temporal coverage. We've never had this two-frequency system that's covering so much of the Earth. But we really are, the science community is absolutely thrilled about having this system. If you hit return again. I can't emphasize enough that this would not have happened without this partnership with ISRO. NASA simply wasn't going to do it. No other partner stepped up to the plate. ISRO was there. They were bold. They partnered with NASA when NASA can often be very difficult to work with. So they really stepped up to it, and NASA took the opportunity as well, and it was a fantastic partnership. Totally enabling for this world-class mission. Next slide. One step. Yeah, so I don't want to go into too much detail, but as you can imagine, given that we are on opposite sides of the Pacific and we have very different development cultures at NASA, very rigid, requirements-driven, and process-oriented, and ISRO has a much more agile development style for their missions than we do that is usually much more characterized as a just-in-time approach. Not quite like that, but you can think of it that way. There were often requirements on our side that ISRO didn't understand and wasn't ready to address. So we had to come to an agreement repeatedly throughout the life of the development to figure out a way for us to meet our sponsors' requirements and ISRO to be able to execute on the many, many missions they were doing in parallel while we were doing this mission. And this development took 10 years. 10 years is twice as long as most ISRO developments take. And that made it a real challenge for getting this to work. But by doing the things we did, going there, becoming friends and colleagues with them, interacting on a social level as well as a technical level,
and showing due respect to the processes on either side, we somehow made it work. And we were very happy, very fortunate. I think there's one more time step. Yeah, and this is the point. Strong relationships are essential for making these partnerships work. This picture you see here was the last science team meeting that we had at URSC ISIT, their integration facility. And it's not just scientists in that picture, it's all of the integration test engineers, all of the other people that we had working on the spacecraft at the time. It really took a community to build it, and it was a real pleasure to be, and privilege to be involved in it. So thank you for listening. I hope that was enjoyable.
Thank you, Paul. We got a few minutes for check. Okay, well, one way or another. So we've got 5 minutes or so for questions tonight. I've got one, and you mentioned you're on a 6 p.m. 6 a.m. orbit. So you map through, oh, there we go. Now it's working. You map the planet in 6 days. Over the course of 12 days, you map the planet twice. Once you're looking at it at 6 p.m. local time, sunset. The other time it's sunrise. And at first I was going to ask you why that was scientifically, and then I thought, oh, it's the solar panels. You want to make sure the solar panels are always looking at the sun. But then I was thinking maybe there is something that changes between sunrise and sunset. Could you comment at all on either of those?
Yeah, so you're right. It's partly power. We use a lot of power, so having access to the sun at all times is kind of important for this mission. But the other main reason why we wanted 6 a.m., 6 p.m. is the ionosphere. So we are at L-band, and L-band is a long wavelength that does interact with the ionosphere more strongly than at shorter wavelengths. And it turns out that the ionosphere is least active at 6 a.m., actually 5 a.m. is sort of the least active time. And it's not at its maximum activity at 6 p.m. So that's 6 a.m., 6 p.m. is a good time to image if you have a long wavelength radar and you don't want the ionosphere. It turns out, by Murphy's Law, that we are now at solar maximum solar activity. The ionosphere is just cooking, and it's really messing up a lot of the data. But we have designed, we knew that the ionosphere would be an issue. We have algorithms that allow us to do a GPS-like processing to remove the ionosphere from the data. Scientifically, having the same time of day, whether it's morning or night, is always beneficial to remove one more variable from the
I mean, this is maybe a reach, but is there any signature that's detectable because of the thermal difference in you're looking at sunset, the land you're looking at has been heating up all day, and you're looking at sunrise, it's been cooling off all night. Does that produce any detectable changes in any of the?
Yes, the answer is yes. There's several factors. One is the atmosphere itself. If you're interested in atmosphere perturbations, propagation of the signal through the atmosphere and back, which also affects our measurement, it's much worse in the evening. Often the surface isn't moving, so we are an exquisite water vapor detector. And so that's one thing. You can look at differences in water vapor content morning and night, and that is interesting for climate weather modeling. But soil moisture changes are very different in morning time and evening time, and using that difference is a great way to calibrate your algorithm, actually, to see whether you're actually measuring it. Trees respond differently across the day, so they have a different state at night than they do. It's just like people. You're more awake in the morning, less awake at night. And for deformation, the heating can actually cause buildings to expand and crack. So you'll see a different signature at night